This lesson will cover the second derivative test, which is how we test for concavity. This is in section 3-4. First, let's talk about what concavity means. Concavity is, think bowls. It's like a bowl, both concave up, where the graph of f is increasing on an interval, or concave down, when the graph of f is decreasing on the interval. This is usually easier to see in an actual picture. This is concave down, because notice that the curve is going down, facing down. This is concave up, because the curve is facing up. I like to think of it as when you're having a down day, you're frowning. When you're having an up day, you're smiling. So the second derivative test is what allows you to figure out if the original function is concave down or concave up. Inflection points are points on the actual original curve where the graph changes its concavity. So notice this is concave down, and then it becomes concave up. And then this is concave up, and then right here it becomes concave down. So the second derivative test, this is very important, as you can tell, because I put a million stars next to it. If f is a function, so that the first derivative equals 0 at some x value c. So at this x value, whatever it is, the derivative equals 0, which means we have a maximum or a minimum. Then the second derivative of f, provided that it exists, will tell you is it concave up or concave down. If the second derivative is positive, then the original graph was concave up. If the second derivative is negative, then the original graph is concave down. This also goes with what we were talking about the other day when I made you find all the different, with this that we did the other day, where I made you graph it. Let's look and see what it says. Remember, here's the original function. That was the original function. This was the derivative. So recall that the derivative, when the derivative is positive, then the original graph is going up, has a positive slope. When the derivative is negative, then the original graph has a negative slope. Now let's look at the second derivative. This orange line here is the second derivative. Please note where the second derivative is positive and negative. Let me darken the line a little bit. So notice right here. If I were to cut the original graph in half right there, notice that when the second derivative is negative, so when it's below the x-axis, we have a concave down, so a frowny face for the original graph. Note that when the second derivative is above the x-axis, so when it's positive, we have a smiley face, so concave up. So when you look at the second derivative graph, wherever it is below the x-axis, that tells you that the original is concave down. Wherever the second derivative is above the x-axis, that tells you where the second derivative, where the original is concave up. Let's actually apply these things to an example. So we're going to look at example number 1. It says, find all relative extrema. Well, remember, extrema just means maximums and minimums. So first we're going to find all the maximums and minimums. Use the second derivative test where applicable. So apply the second derivative test if you can. And then they give us the function negative x times x minus 5, all of that squared. Okay, first we need to find maximums and minimums. Remember, maximums and minimums is when f of f prime of x equals 0. So when the first derivative equals 0. So we're going to actually have to find the first derivative. This is going to be a combination of the product rule and the chain rule. So first derivative. You let this be the first piece and this be the second piece. So first times derivative of the second. So chain rule. Bring that down. The outside times the inside. Plus the second piece times the derivative of the first. Let's clean this up because it looks kind of ugly. We have negative 2x times x minus 5 minus an x minus 5 squared. I'm going to clean this up a little bit more because I know if I set this equal to 0, I'm probably going to have to wind up foiling and all that fun stuff. So I'm going to clean it up more. Note, there are two terms. Both terms have an x minus 5. So I am going to factor out 1x minus 5. And then I'm going to leave behind this negative 2x minus one of these x minus 5s. I'm going to distribute this negative and then combine my like terms on the inside of this parenthesis. So I'll have that the first derivative equals x minus 5 times, and then this is going to be negative 2x minus x, so negative 3x, and then two negatives make a positive. This is much easier to solve when I set them both equal to 0. So x minus 5 equals 0, and negative 3x plus 5 equals 0. So this is x equals 5, and this is x equals 5/3. So these are my critical numbers. The places where I have maximums or minimums. Let's actually find out which ones I have. To do that, I'm going to do the first derivative test. So remember, this is where you draw your interval line. I'm going to break it up with a 5/3 and a 5. And I'm going to pick numbers in between these. Like, I'm going to pick 0 over here. I'm going to pick 6 over here. And I'm going to pick 4 right there. It doesn't matter what I pick. I'm just going to pick something within the interval. Remember, this is going to negative infinity. This is going to positive infinity. When I plug 0 into my derivative, I get a negative number. When I plug 4 into my derivative, I get a positive number. Again, it doesn't matter what the number is, it's just the signs we care about. When I plug 6 into my first derivative, I get a negative number. So my graph is going down, and then back up, and then back down. So right here, I have a minimum, and right here, I have a maximum. So we have a maximum at 5, find your y value, and a minimum at 5/3, find your y value. I'm going to let you plug those in. Now it says use the second derivative test where applicable. So remember, this is the first derivative. We are going to have to use the product rule to take the derivative the second time. So second derivative. First times derivative of the second plus second times derivative of the first. Start cleaning it up. We get negative 3x plus 15 minus 3x plus 5. Combine your like terms. We get negative 6x plus 20. So that's our second derivative. Again, the second derivative test, you first have to find what are called inflection points, those points where it changes from concave up to concave down or vice versa. So to do that, you need to set this equal to 0 and solve for x. So I find that x equals 10 over 3. So this is an inflection point. And then just like the first derivative test, we are going to have to create a number line to see if it's concave up or concave down. I'm going to pick two numbers on either sides of this. So on this side, I'm going to pick 0 because why not? It's the easiest thing to plug in. Why wouldn't I plug that in? And on this side, I'm going to pick, I don't know, 5. Let's go with 5. Okay, I get a positive number when I plug 0 into my second derivative. I get a negative number when I plug 5 into my second derivative, which means this is concave up and this is concave down. You can check yourself by making sure. Look back at the first derivative test. Right here, is this not concave up? So roughly in the same interval, notice that these are roughly the same interval. This is concave up because there's a minimum, and this says it's concave up. This says that it's concave down, roughly in the same interval, that this is concave down. So then we have an inflection point. So inflection at 10 over 3, find your y value. So there you go. We did the first derivative test and found the maximums and minimums of the original function. We then did the second derivative test and found where the original graph was concave up or concave down. Let's move on to the last example. We're going to sketch the graph of the function having the given characteristics. Let's see what all of these things mean. Start with this part. F of 0 equals f of 2 equals 0. Well, what does that mean? Remember, this and this are an x value, whereas all of this means that when you plug 0 in, you get a y value. When you plug 2 in, you get a y value. And they're saying those y values are 0. So basically, they gave us 2 points. 0, 0, and 2, 0. So these are x-intercepts, where it's going to hit the x-axis. Let's look at this right here. It says the first derivative is less than 0 when x is less than 1. Well, remember, if the first derivative tells us slope. So this is saying that before we get to x equals 1, so when x is less than 1, the slope is negative. Agreed? Right here, it says when x equals 1, so when x equals 1, we have a slope of 0. Remember that when slopes are 0, we're going to have a maximum or a minimum. When slopes, so when the first derivative equals 0, that's a maximum or minimum. This x value says, well, that max or minimum is happening at 1. Last part, this part here. They're saying the derivative is greater than 0 when x is greater than 1. So when x is greater than 1, the slope is positive. So the graph is going up. Last thing, they're saying the second derivative, the whole thing, is greater than 0. That means our entire graph is concave up. The whole thing is concave up. So let's start drawing what we know. We know that we will be crossing the x-axis at 0, 0 and 2, 0. So there we go. We know we're crossing there and there. We know that our graph does different things when x equals 1. Alright, when x is less than 1, they say the slope is negative. So we must be going down. They say when x is greater than 1, so on this side, our slope is positive. So our graph has to be going up. So we have to be approaching this x-intercept and then going away from that x-intercept. There must be a maximum or minimum at x equals 1. Well, since it's going down and then coming back up, it's obviously a minimum. Where? We're not sure. They don't give us enough information. This is a rough sketch. So we know we're going down, curving, and then coming back up. The second derivative says that the entire graph is concave up. Well, is this not the entire graph, and is it not concave up? So there you go. I hope you enjoyed this video. We will be practicing both the first and the second derivative test tomorrow in class.